Okay, what's up guys? So if you followed me yesterday on my live stream in the evening, you will have seen me doing a long ass repair on this Solid Audio F2500D. So this is a 2.5k amplifier. It kind of almost won't do 2.5k at 1 ohm, but it all should do it at 0.5 ohm. It's not a 0.5 rated amplifier, but I think this amp was designed with 0.5 ohm in mind. So that, yeah, basically people could run it down at that low impedance and it would do a good amount of power. It's got some pretty nice components inside. We have got P channel and N channel MOSFETs in this amplifier. So this uses a high voltage rail and a low voltage rail to swing the audio between, rather than just a high voltage rail and using N channel MOSFETs to do the whole thing. Uses N channel and P channel MOSFETs. So this amplifier had a dead power supply section, a dead power supply drive section, and dead outputs. And the reason it had dead outputs and the reason this amplifier blew in the first place was because we had a problem with one of the traces on the board going to the gates of one of these low side MOSFETs. So what happened is the trace just broke, made a poor connection, probably from the previous repair, and probably vibration on the box caused this trace just to come away from the pad here on the low side drive gate pad, and then this side wasn't being driven, and so it blew and the amplifier went down and it took the power supply along with it, which is no fun whatsoever. So what we're going to do is we've made a full repair of this. I've loaded her up with original parts. I was going to use some 12P20 fets. However, I found that the RDS is all over the place, which means that they've been got from a bad source. They're a bad batch from factory. The RDS is all over the place. So I don't want to use those because we could have more issues going forward if we use those fets that aren't very good. So I found some very good original 9640 and 640N MOSFETs to load this amplifier up with, and we've got 064Ns in the power supply section. So it's all standard. I have thickened up some of the traces on the bottom of the board, so let's see how much power this does. We've got our 12 volt power supply going in here, and let's turn you onto the scope view so you can see how much power this thing does. I have recently bought myself a pretty nice fancy frequency generator, function generator up here. So I've got about 50 hertz going on there. It's quite hard to get this accurate, to get it bang on 50 hertz. 49, 50. It's like when you're at the petrol station, you're trying to put exactly 20 quid in. There you go, 50. That's good enough. So scroll back down to our scope here. So what we're going to do is power this up and see how much power it does. I've already calibrated this pretty much into clipping, so you'll see what it looks like on the scope screen. Okay, let's hit the test and see what the wave looks like. So you can see there, I'm just going to tap it up a little bit into clipping. Okay, so you can see that we've got a tiny little bit of soft clip on the top of the wave there, just a very, very, very faint misshapen of the wave on the top there. So what we can do is we can use that. That is probably about 1% THD, looking at that. So what we can do is take our calculator here, and we can work out how much power that did. Good afternoon to Taka73. Okay, so we have 35.86 volts. That was at 1 ohm. So to work out 1 ohm, we times that by itself, 35.86 times by 35.86 equals, so that is 1285 watts at 12 volts at 1 ohm. So now we just need to correct that for 14.4. Our correction factor is based on square law, so we take 14.4 volts, divide that by our 12 volt power supply, and we didn't get any voltage drop on there because these power supplies are very, very strong, and I know that benching this amplifier would cause no voltage drop. So we got 12 volts on the power rails here, so 14.4 volts divided by 12 volts, that comes to 1.2, square that, I get 1.44. So if we times this by 1.44, that is our square law correction factor. So 1285 watts RMS at 12 volts 1 ohm times by a correction factor of 1.44 equals 1,851 watts at 1 ohm. That is consistent with what I have seen from these amplifiers. So a solid audio 2500D, you think, it should do 2.5k. It's not a 2.5k at 1 ohm. It's about 1800 watts, so we've got 1851 watts RMS at 14 volts 1 ohm, which is about right. Now what we're going to do is we're going to try a 0.5 ohm test. So to do that, because I don't want to buy a crap load more dummy loads because they're expensive to import, we've got an old voice coil here. This is a 4-inch voice coil from a DD9912. And we've got this wide in series. This is a woofer that had a dead spider and some other problems with it, but the coil is actually fine. So it's a 4-inch coil from a Digital Designs 9912. It's a dual 0.5 ohm coil, so we series the coil up so we have a 1 ohm load here. This is a 1 ohm load, and we can just run that in parallel with our dummy loads here, which are also wired down to 1 ohm, because 1 ohm and 1 ohm in parallel equals 0.5 ohm. So obviously this coil will heat up a little bit, but it's only a very, very short test, so we can get away with a little bit of heat on there without it changing the resistance. I just need to trim the end off this. Let's trim the end off this wire. We've got 10 people currently watching. This is only going to be a very short live stream this time, because we're just doing a bench test of this amplifier. So what I'm going to do is I'm going to stuff these in the ends here along with the dummy loads. Give it some juice, says Timmy. Yeah man, we're going to give it some juice at 0.5 ohms. So this should do about 2.5k at 0.5 ohms, fingers crossed. Once we finish this bench test, obviously this is a repaired amplifier, so it goes through my bench test procedure, which is what we're doing now. Provided it makes decent power and it doesn't blow up in flames on the bench, then we do our endurance test, which is 45 minutes worth of sweeps on a static load and a reactive load at the same time. 1337 IOT says, what's a better amp than the Fosgate T604 Prime? Probably something by Genesis. So we've got the negative in from this voice coil here. I'm just going to put the positive in. So for those of you who have just joined us, we are testing on a reactive load. What is an active load? So Timmy says, what is an active load? So what we're doing is we're testing on a static load and a reactive load. A static load is just a resistor that doesn't change in value when you drive it. So a dummy load, a big resistor like this, when you drive it with power, it's still 1 ohm. A reactive load is a load that changes its impedance, its resistance, when you drive it. That being a subwoofer voice coil in a motor. If you don't understand impedance rise and you want to understand a bit more about reactive loads and static loads, watch my video on my channel entitled What the hell is box rise and why it helps. I've got a video on box rise which talks about static loads and reactive loads and why the load changes when you apply power. So we're almost done installing our 0.5 ohm load. How's it going, Corey? From the USA. What time is it in the States now? Must be about lunchtime. Am I right? So we're going to put our 1 ohm load on there. And let's plug our scope back in. So 0.5 ohms. What are we going to see? Are we going to see a big explosion on the bench here, guys? Or are we going to see some power? 7:30 AM? Really? What country is that? It can't be. What the fuck? It must be miles away from me. It's like flipping. It's 3:30 in the afternoon here. So let's reset our scope. Los Angeles. 10:30 AM Eastern. Wow, damn, fair enough. It's still early as fuck. This is annoying, see, because this is like during the day that I'm working, and obviously not a lot of people will get to see this, this live anyway. Well, 21 people watching, that's not too bad. So yeah, 0.5 ohm load. Let's get this hooked up then and see what the jam is. See what the jam is with 0.5. And for this, I am actually going to hook up my multimeter to the power inputs to see if we get any voltage drop, because I'll take that into account when we're working out the power. Because these power supplies are pretty good, but they might actually drop some voltage here with this crazy low impedance. Now, those fans are crazy loud, aren't they? Those fans are crazy loud. Okay, so let's do this then. I'm slowly bringing it up. I don't want to run this amplifier too hard at 0.5 for too long. I think we're getting near clip point. Getting near to clip point. There we go. There's our clip point, and you can hear the amplifier really struggling there. Okay, so that's actually not a lot of clip. That's actually not a lot of clip. I'm just going to give it a tiny bit more power. Tiny bit more power. There we go. That's our clip point. So that is a respectable clip point for 0.5 ohm load. That's probably about between 3 and 5% THD. So we're doing a 3 to 5% THD test at 0.5 ohms. And how hot is this dummy load? That's not that hot. That's literally is just very lukewarm. So the resistance of that won't have changed much. Ah crap! I didn't actually test what was our voltage drop there on the multimeter here. What was our voltage drop at that level? $11.84. Okay, so we've got 11.84 on the voltage drop. So let's take our calculator and work out how much power that did. I think we're going to see some good power here, guys. That was still 32 volts. This is a good little amplifier, you know. The Mart Sakis says, "Hey Sam, are you repairing straight from last night?" Yeah, this is the Solid Audio 2500D that we repaired last night. We actually got it working fully last night, but we didn't have all the output MOSFETs fitted in. We just had one per bank. And so, yeah, the repair was good last night. It worked fine. So I've loaded her up with all fresh MOSFETs on the power supply and the output section. And as we've seen here with this bench test, it seems to be doing pretty good power. So let's take our calculator then. So what we need to do is we need to take 32.39 volts, which is what we saw on the scope there, on the scope screen. Can you see that? So there, the scope screen, we've got 32.39 volts RMS. And because it's a 0.5 ohm load, we need to double that. So we times that by itself, and that gives us our current. So the current that we saw, that this amplifier just did on the output section, was 64.78 amps on the output section. So we times that by the voltage that we saw, times that by 32.39, and that gives us our power. So this thing just did 2098 watts at 11.8 volts of input. Okay, 11.8 volts of input at 0.5 ohms. Not bad. So let's use square law correction factor to work out what that would have done at 14.4 volts. So 14.4 divided by 11.84, which is our voltage drop that we saw, times that by itself. This calculator is screwing me over, so sorry. 14.4 divided by 11.84 equals times by itself 1.21621621621 recurring. So our correction factor is 1.479. So we times that correction factor by the power that we saw at 11.84 volts. So 1.479 times by 2098.44 watts equals, whoa, 3,103 watts RMS, 14.4 volts, 0.5 ohms. That's a crazy lot of power, guys. That's fucking wicked. That is wicked. Very nice indeed. That's a huge jump from the power that we saw at 1 ohm. So we had 1,800 watts at 1 ohm. Usually it doesn't jump that much with the 0.5, but this amplifier is obviously designed for 0.5. So yeah, pretty epic stuff. And we can see, if we take our multimeter, we can see that we are loaded down to 0.5. So our test load resistance on here is, of these test leads, let's give you a wiggle. Test lead resistance is 0.7 ohms on my multimeter resistance. Let's do that screen there so you can see. So my test lead resistance is 0.7 or 0.8 ohms. And if we now attach it to here, the speaker outputs, on the meter we have 1.4. So 1.4 minus 0.5 is the test lead resistance that we saw. So this is a static 0.5 ohm load. This is the most stressful environment that you will ever see an amplifier play into. When you connect this to a subwoofer, you have impedance rise, and it will never see that lower of an impedance. So what we just did here with this test, we put this amplifier under the most stressful environment that it could ever possibly be subjected to. A 0.5 ohm load, 11.8 volts worth of input, and it chucked out over 2,000 watts RMS into 11.8 volts and over 3,100 watts RMS into 14.4 volts. Wicked stuff. So that is a successful repair. Successful repair, very successful repair. I'll do the endurance test, and that will then show up. Obviously, the endurance test is the main thing that we want to do to make sure that this amplifier is good going forward. But yeah, once we've done the endurance test, this should be good to go back to the customer. So yeah, a short little video for you guys. Hopefully it is interesting for you to see the bench test process, and I will be back with you probably tomorrow because I am busy this evening, and we're going to start looking at, what have I got on my to-do list over here. I've got a massive, great big part. You can see there I've got this shelving unit up here. This is my to-do list. So I don't know, I'll have a look through that and work out exactly what we've got to repair next. But yeah, I shall see you tomorrow. Thank you very much for tuning in once again, and have a good day.